Dr. Wolfgang Herrmann, and he's going to give a talk on his fast radio burst observations at Astropeiler Stockert. Wolfgang is president of Astropeiler Stockert. Yeah, I get that right. A nonprofit organization of volunteers operating at the Astropeiler Stockert Radio Observatory in Germany. Received his PhD in physics in 1979 from the University of Bonn. His professional career has been primarily in the telecommunications industry. He's now retired, enjoying working in the field of radio astronomy and trying to make the best use of the instruments of the observatory, which includes a 25-meter dish. His presentation will give insights into this great instrument. The other thing I'd like to bring up is Wolfgang has been very interactive in the forum, and has it doesn't seem like there's any problem too small to for him to provide insight on how to improve your systems. So if anybody's not on listserv now, if you want to have a conversation with Wolfgang offline, the listserv seems to be a great place, and he's on there a lot and has helped a lot of us amateurs. Okay, the floor is yours, Wolfgang.
Well, thanks very much. Good morning, everybody, or good afternoon, wherever you are. Let me share my screen. So what I'm going to talk about is fast radio burst observation, which we did for quite some time at our observatory. And I would like to essentially make two parts of this talk. The first part will be about what are FRBs, what can you observe, what are the characteristics, and what is the enigma about fast radio bursts. And the second part will then dive into what we have observed and how we do the observations. So let's get started. What are fast radio bursts? These are, simply speaking, single pulses that come up out from the sky. And they were first observed by Duncan Lorimer. So the first one was also called the Lorimer burst. And it just happens that I think 2 or 3 or maybe 4 days ago, it was the 20th anniversary of this detection. So it's relatively new, but also sometimes you're surprised it's already 20 years ago. So what did he observe? He observed a single pulse. And the specific characteristic of this single pulse was that it was broadband and it was dispersed. Dispersed meaning that the arrival time was varying with frequency, like shown in this plot. This is the plot from the original publication. So the 1.5 gigahertz arrived earlier than the lower frequency. And this is very characteristic of astronomical sources, also pulsars, when the pulse propagates to the interstellar medium. Now, the point about this one was that this dispersion was so large that it could not be explained by our galaxy, by the characteristics of a galaxy. And I explain that a bit in the next slide. So what happens is, let's take this picture. Assume that we have something which generates a burst in a different galaxy, like here. Then this burst, this wideband burst, will propagate and eventually will arrive at your observatory. Now, the delay between the higher frequency and the lower frequency, I denote this by the blue and the red line, is dependent on the density of charged particles along the line. And if you observe a delay which is larger than what can be explained by our own galaxy, then you know it has to come from outside of our own galaxy. The contribution from our own galaxy, our Milky Way, is known relatively good. There are models which describe the electron density. So if you're looking in a certain direction and you get a signal that has a higher dispersion, you can conclude it must come from a large distance. So this is essentially the finding that was behind the Lorimer burst, or the first fast radio burst. Now, what are these fast radio bursts? The first idea was that it are probably some kind of catastrophic one-time events where maybe two neutron stars collide and merge, or something very dramatic. And it actually has to be dramatic because of the large distance. You observe a single pulse with your telescope, and you notice coming from far away, like maybe many millions or even billions of light years, and it still gives you a signal. So it must be a very intense event. And people originally thought, well, this can only be something where things are destroyed. Now then, there was a surprise because Laura Spittler detected a repeating FRB. Actually, when the first were detected, people were trying to see, are they repeating and so on. It was never observed, but then Laura found something in the survey data from the Arecibo telescope. The one is called FRB 121102, which denotes the time of the event. And this, of course, puts things upside down. So if it's repeating, it cannot destroy itself. So is that what's behind that? Now, since that first detection of a repeater, there have been more repeaters detected. And there has been another detection that some repeaters show episodic behavior. What does that mean? You see a number of bursts. They're not that frequent, but there are a few bursts, and then it stops, and then it comes up again. Pulses come up, and then there's again a pause, and then they come up again. And this has a repeating pattern. So there are some which occur every 16.5 days, others are 160 days or whatever. So this is something which has been detected over longer time observations to see when do bursts occur. So this is a question mark, what's behind that? Now, how many FRBs are actually known? And this has changed quite drastically recently. As of May, there were 147 FRBs known, so one-time events. And including in this number were 25 repeaters, so FRBs where several times such a pulse did occur. But even in May, it was already known that there are quite a few more which were not published yet. There's this telescope in Canada called CHIME. I think that stands for Canadian Hydrogen Intensity Mapping Experiment. As the name suggests, was originally designed for something else, but it's now an excellent instrument to capture fast radio burst. So everybody and his brother knew, well, there are more than this 147. They just haven't told us yet. And in June, there was the first data release from the CHIME FRB collaboration, and they said, okay, it's now up to 607. Why didn't the number of repeaters go up? As you can see, it's 24 in May and 24 still in June. Well, that's simply due to the fact that the CHIME people have already published their repeaters in advance. The publication covers only detections up to July 1st, 2019, and there's a second data release still coming. Don't know when they're going to publish it, but it's probably not far away. And I believe that's probably going then up to something like 1,000 FRBs that have been detected to date. So quite a number of things which started with this one single Lorimer burst. Okay, these are the detections that are known as of today. Another question is also important for amateurs: how strong are these FRBs? They have quite a large range. Mostly are fairly weak. The range is from 10 milliansky and up to 100 Jansky. This is the peak flux, and another important parameter is the fluence, which is the total energy in the pulse. So it's sort of the curve under the pulse shape. And this can be something like 10 milliansky milliseconds up to a few hundred Jansky milliseconds. And if you look at those numbers and at 25 meter dish, we know that most of these FRBs we cannot see with a 25 meter dish. These are detections which are done with the 100 meter class telescopes or the used to be Arecibo or now FAST, the big in China. But if you're talking about a couple of tens or maybe starting 10 Jansky milliseconds, then we are getting into the ballpark of our 25-meter dish. So it's not something that is completely out of the question of a 25-meter dish. Okay, since we knew that there is a fair or a reasonable chance that we can detect something, we thought about what can we do about it. Okay, that's something I should mention before I dig into that. There's something interesting which is called the SAT trombone effect. This occurs in fast radio bursts, and in particular, it does occur in repeating fast radio bursts. The effect is that there are several pulses in a short time period. We're talking about, in this case, about 20 milliseconds. So it has a certain structure, but the frequency which is covered by this pulse changes. It goes from higher frequencies to lower frequencies. And this is a effect which was noticed. It was called by SAT trombone as SAT trombone because you sort of make an audio from that, you get something like wah, 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 wah. So this is why it's called the SAT trombone. As I said, the point here is that is observed in repeaters. And the question, I'll come to that, is it always a repeater if you observe a SAT trombone? Then another thing worthwhile mentioning is something that happened, if I recall correctly, in March or maybe April of 2020. There was a detection of a extremely strong pulse. It was detected by the CHIME telescope, also by another smaller telescope, and also by an experiment called STARE-2. This event was so strong that the detection by CHIME was in the complete side lobe, so they didn't look in that direction. It was soon detected that the source of that was a magnetar in our own galaxy, so it's a galactic FRB, if you want to say so. Because it was a side lobe detection, one can only roughly estimate the fluence. It was something like 500 kilojansky millisecond, maybe even 1.5 megajansky millisecond. So it was an extremely intense pulse. And people were considering, well, if it's that extreme in our own galaxy, could this be also the source of these fast radio bursts if they're in another galaxy? If you make the calculation, say, okay, if this magnetar would have been in a different galaxy, would that have a signal equivalent to what we see in the extragalactic FRBs? And the answer is, well, not quite. There's about a factor of 10 missing, but still it's a strong indication that magnetars might be a source of these FRBs, but it's not confirmed, and a lot of discussion is ongoing. So there are quite a number of mysteries around these FRBs. And when it started, when Duncan Lorimer observed the first one, and more were found and so on, people started making theories. What could be the progenitor of that? What happens there? And within a short time frame, many theories came up. Some people were joking, well, we have more theories than we have actual observation events. And it was true for some time. There were something like 50 different theories and maybe 30 observed FRBs. Now, things have changed a bit with a couple of hundred FRBs. All these theories are, yeah, I mean, there are just many ideas. Some are quite credible. Magnetar, as I mentioned, is one of the potential sources, but then there are also some very strange ideas. Someone have argued that these are aliens firing a maser at something to propel it, something like a light sail kind of thing, propelling their equipment. Well, anyway, that's a little bit unusual theory, I would say. But the basic question is still, what are FRBs? Then the next question is, if there are repeaters and there are non-repeaters, is this actually the same type of source? Maybe we have two different populations, one kind of astronomical event which creates these one-time FRBs, and a completely different thing that creates the repeating FRBs. Well, that's an open question. Some speculate, well, maybe all FRB are repeaters and we just haven't looked long enough. That's quite a possibility. Then what's open still is if you have a repeater, I explained some have an episodic behavior. Do they all have an episodic behavior? Because the time frame differs quite a lot, and it takes a lot of observation time to determine whether something has an episodic behavior. Of course, an interesting question is, what's the process behind the sad trombone effect? What happens there physically so that you get the sad trombone? And I mentioned that sad trombone have, as far as we recall, only been observed in repeaters. So the question is if you observe a sad trombone in an FRB, is this a reliable indicator that it is a repeater? So you can go and watch. And you may have seen in some of the plots, let me go maybe, yeah, let's stick with this one. You can see that the spectrum is confined. It's not going through all the bandwidth. And this is something that is observed in many of the FRBs. They do emit broadband, but they don't emit like the pulsars do through all the full spectrum, like from 300 megahertz up to the tens of gigahertz. So typically are spectrally confined. And this is another question. Why is the spectral distribution confined? What is it, again, the physical process? What does it tell us about the physical process, the fact that it is confined? Okay, so there are quite a number of mysteries and question marks behind that that need to be solved. And we were asking ourselves, what can we do with our instrument to solve the mystery? Our instrument means this 25-meter dish here in the foreground. And we operate that in L-band with 100 megahertz of bandwidth. Just for sake of completeness, there's another dish on our premises. This is a 10-meter dish, which we operate in the 10 and 22 gigahertz range. And we also have two other smaller L-band dishes, a 3-meter and a 2.3-meter dish. The 2.3-meter dish now sits here. It's not on the picture yet. It's your newest instrument. Anyway, so FRB is a thing just for our big instrument, and this is what we are using. We started the whole exercise in 2018. The idea was, of course, what can we do with FRBs? And the first idea was we could try a blind search. The idea behind that was, since FRBs are extragalactic, there is no reason why they are here or there. They can be anywhere in the sky. They are not in the galactic plane, they're outside, and they can be anywhere. And if they can be anywhere, it doesn't matter where we look. So we can look at any place, we just have to be lucky. So we thought, why are we not just going and collect data while the telescope is standing still? So just let the sky pass and use that time and collect data. And that's what we did. The problem with that is if you do a blind search, you're looking for a pulse and you have no idea of the characteristics. In particular, don't know what the dispersion is. So you need to try all reasonably thinkable dispersions. And this is a very compute-intensive job. So we used a GPU-powered pipeline. GPU is a graphic processor. And there's a program not developed by us, by others, by the professionals called Heimdall that does that. We ran this program from August 2018 until March of 2020. We collected some 3,600 hours of observation time. That gave us 35 terabyte of data. And this also shows the challenge. If you have 35 terabyte of data from 3,600 hours and you're looking for a millisecond event, there's a lot of data to look through. And of course, you get a large number of false events. So you get a detection indicated by your software, and then you have to make another filtering to throw out the obviously wrong result, and then you need to inspect the remaining things. That's a lot of work. But anyway, we did that, and it ended that we did not detect a FRB in this observation run, which is quite reasonable because we would only detect very strong ones, and they are not that frequent. So it was just giving chances, and the idea was when the telescope is standing still and not used for other purposes, why not do it? If we don't look, we don't see anything, and if we look, we might eventually see something, but okay, we didn't see. The next thing that we did was a little bit more targeted. When the repeater came up, this FRB 121102, we looked at it, and we looked at all the pulses that were detected so far, and we said, okay, all of these are too faint for us. Even though we had been looking at this source at that point in time, we would not have seen it. We were not big enough, we have too much noise. But the speculation was that, well, eventually there might be some brighter pulses. So if we're just lucky and collect data, we may be detecting something. We discussed it also with a lady who did the original detection with Laura Spittler, and she encouraged us to do that. So we ran a one-year program, essentially, because then we had to track, we had to keep the telescope moving and track on target. So we collected some 180 hours of observation time, 1.7 terabyte of data. This time the analysis was a bit easier because you already know what the dispersion is. You can specifically look for pulses which do have that specific dispersion. And again, we had no detection, which was not so unexpected because all the pulses so far we knew were too faint for us, and we just had to be lucky. All right, then there was another repeater which was interesting to us. That's called FRB 180216, detected by the CHIME telescope, and also later on seen by many other telescopes. And this had this, what I mentioned earlier, this episodic behavior. There's an activity phase which lasts for 16.3 days, or the periodicity of that activity phase 16.3 days, and the activity occurs in about a 4-day window around that. So you can target your observation, saying in each of these activity phases you spend observation time looking specifically during this time, and the rest of the time you don't expect to see much. So you can tailor your observation time. And again, this was a project running from January 2020 until April 21. And we'll probably resume this later on. We collected 870 hours of observation, again, 8.7 terabyte of data, and again, no luck. Again, one has to say that this repeater, the pulses that were known also were, I would say, on the low side for us. So the expectations were not that great. Okay, so this was a good try, but we did not succeed. Then there is another repeater called FRB 2020-11-24A. As the name suggests, it was first detected in November of 2020. And this is also a repeater detected by the CHIME collaboration again. It has a dispersion measure of 413. And the interesting thing, what got us triggered on this one was that the CHIME collaboration reported that there's an enhanced activity. They sent out an astronomer's telegram. An astronomer's telegram is sort of an email distribution which you can subscribe to for interesting subjects that you're interested in. And we received this astronomer's telegram saying that this repeater has an enhanced activity. CHIME reported that it had 6 events between March 23rd and March 28th. And the strongest that they had seen was something with a fluence of 5.5 Jansky millisecond. And this triggered us because we said, okay, 5.5 Jansky millisecond, that's very much at the limit of what we might be able to observe. A factor of 2 on top of that would be better, but if it's active right now with several events in several days and getting close to our sensitivity limit, that should be interesting. Not only we thought about that. I mean, as this telegram came out, there was really lots of activities, and we had a report, for example, from ASCAP in Australia, and they reported on the April 1st something with a fluence of 187 Jansky millisecond, and that said, okay, this is in our ballpark. This, if we had been looking at that time, we would have seen that. This is the detection from ASCAP, and I should explain that a bit, what this graph means. It's a so-called dynamic spectrum. The color or the intensity shows the intensity of the signal, and this is de-dispersed. This means it is corrected for the delay at the different frequencies. You can see that ASCAP observes between around 700 megahertz up to above 1 gigahertz, so a little bit more than 300 megahertz. I think it's 33.6 megahertz that they observe. And you can see it's, again, a confined spectrum. Again, this is de-dispersed. And you see a very nice signal. This is the profile of the pulse. There was another report from ASCAP on April 2nd, where they had, again, 22 Jansky millisecond, which is also in our ballpark. The FAST, a very big telescope, reported they see more than 100 bursts in 5 days. They didn't give any details. There was an S-band trial by the Deep Space Network Goldstone antenna with no detection. The Very Large Array had a detection at 2.4 gigahertz, and Effelsberg had also looked at higher frequencies with no detection. So this was very exciting for us. Okay, we are observing with our 25-meter dish an L-band, 100 megahertz bandwidth, and we had spent, we immediately started when we saw the astronomer's telegram, and we had 90 hours of observation until the 15th of April. And we had a number of events which were in the category of maybe, maybe not, no, don't think so, well, maybe. This is the kind of thing where you're scratching your head, but was not something really convincing. But then we got this one. This was on April 15th. And this is our, again, a dynamic spectrum, as we have seen before. In this case, it's running from 1330 to 1430 megahertz. Again, de-dispersed. And you can see it goes all across the band. You do see parts where it's brighter and parts where it's dimmer. This is expected. This is scintillation from our own galaxy. So that, again, this is actually a confirmation that this is a astronomical signal if it has a clear scintillation. And we measured a dispersion of 413, which is exactly the expected number. We had a signal-to-noise ratio of excellent signal-to-noise ratio of 85, and our peak flux density was determined to 215 Jansky, and a very large fluence of 334 Jansky millisecond. So an excellent signal. This is another representation, a Czech representation of the dynamic spectrum. In this case, it's undispersed, so you can see the delay across the band. And the red line is a comparison line. This is a theoretical line for the dispersion. You may recognize that it is slightly curved. This is exactly what is expected because it's called quadratic behavior. So this is a clear indication that this is a clearly dispersed signal. A question, of course, comes up: how do we calibrate? I gave you numbers for the fluence and the flux density. The way we do this is that we make a transit scan of a known source. Transit scan means we put the telescope at a position, let's say, before the source, and then stop the instrument, and the instrument will then transit through that. So over time, we get an increase. So the source comes in, and then it goes out again. And these are sources which have a very well-known flux density. In this case, it was a radio galaxy 3C123. The flux is known. So we know an increase by this in our machine values is an equivalent of 48 Jansky. And this then we can use to look at our pulse. So this is the pulse that we have received. We can determine the amplitude of that, and therefore we know it's 215 Jansky. It's about, given all the errors for the calibration, that's an uncertainty of about 10%. Okay, some other determinations that we did, width and so on. We did an astronomer's telegram ourselves, where we said we have seen something extremely bright with our telescope. This is something we were proud of, that we had a telegram which was accepted. And then we were lucky again on the 15th of May. This is a burst which has a little bit more complex structure. It has a main pulse and a pulse afterwards. In this case, it's slightly different DM that we measured, but it's still within error margin. Better signal-to-noise ratio, 447 Jansky, and a whopping 1200 plus Jansky milliseconds, so in excess of 1 kilo Jansky millisecond. So it's really, really bright thing. And again, we did the check with the curve, and then we said, okay, if it's that bright, how does that compare with other known strong FRBs? So we looked at it, and I think these are the brightest that we could find in the fluence with up to 400 Jansky millisecond. And the peak flux density, the brightest here, was 161 Jansky. So our first one had a brighter peak flux density than all the previous ones. And this one is brighter in both aspects. And we believe this one, which we detected on the 15th of May, is the brightest and most luminous FRB which has ever been observed. I'm still need to scan through some of the literature, but it seems to be the case. At least it's among the very brightest. And of course, because it's a comparatively to the big instrument, smaller instrument, we'll only see the very brightest ones. So what is the status and what are the next steps? As of July 3rd, we had 670 hours of observation. It has now increased to some 800 hours. Since the May 15th, we had one other but weaker pulse, and one was before the first strong pulse, where we are now convinced that is actually something real. Later on, we will also go on to another repeater. But what this very intense pulse triggered was a cooperation with other instruments. I mean, they noticed that we were doing some interesting things. So we are now doing a coordinated observation with the SARA telescope in Sweden, which is operated by the Stockholm University. Then there's a Torun 32-meter dish operated by the Nicolaus Copernicus University, and one of the instruments in Westerbork in the Netherlands is also used for observing FRBs at the moment. And we coordinated or looked what were our observation times. These are the observation times denoted by these lines here from our observation from end of March, 31st of March until 10th of July. The Torun observed mostly in C-band at a higher frequency. Westerbork looked at the lower frequency band, and Onsala also in the L-band. There's a gap in observation from these instruments because they were involved in the European VLBI network observation, so they couldn't go onto the source, but we continued. And this is an ongoing thing. We would like to continue that. And the bright pulses observed, if we take all these instruments combined, are shown here. This is our first bright one. Then there are a few by the Onsala people. Our very brightest one, which I had shown, was simultaneously detected by Onsala. They were on a somewhat higher frequency, so we now cover more than 100 megahertz, where we know what's going on. Then there's a joint observation or joint detection by Torun and Onsala, and this is our third detection, which is not so bright as the others. Okay, this concludes my talk representing what we do on FRBs. And of course, this is not a one-man show. This is a full team that's standing behind it, and I would like to express my thanks to the team that we have. Obviously, getting all these hours of observation means hours and long hours for people sitting in the controls room and operating the instrument. So it's quite an effort, and I would like to express my thanks to the team. And thanks to you for listening. I'm ready to take questions.
Oh, excellent, Wolfgang. I got a question from Mike Ott. Do the charged particles in the solar wind also cause dispersion?
You do have charged particles, but I mean, we're talking about 8 light minutes from the sun to us. That's a very small distance, whereas when we look through our galaxy, we're talking hundreds of thousands of light years. So the dominating effect is actually from the galaxy. It would be probably a very minor contribution, the solar wind. It probably would not be noticeable just because of the relatively short distance that you travel through that.
Okay. And one from Ed Hartman, I'm going to paraphrase Ed. Assuming that you've got a real dense object in between you and the FRB, could a really small dense patch severely skew the dispersion measure?
Yes, that's a possibility that is also discussed. There is the let's say faint possibility that you have a object that generates this pulse, and then you have let's say a supernova remnant around it, or a patch, as Ed has said, a patch of high density electrons that would sort of simulate the effect of a very long distance. However, you would expect that this maybe happen here and there, but you would not expect that it's happening for so many. But it cannot be totally excluded.
Okay. From Ethan Waldo, if you're not detecting the entire frequency spectrum of the burst, would that have any impact on the calculations?
Yes, definitely. Let me go back to the slide. The values here are related to the full spectrum. Let's say if we were the lucky ones and would have observed only this part of the spectrum, we would have claimed an even higher value, because obviously that's the 447 Jansky is an average over the full observing band. And this also is the reason why one should put these things in perspective if one is comparing one to the other. It's not a one-to-one comparison, because it's always related to the instrumental bandwidth. So in short, the answer is yes, it would influence. Or if we would have observed this part of the spectrum, we would have said there's no pulse.
Okay. From Tom Hagen, have any of these FRB sources been detected in the 10 to 88 megahertz range?
No, to the best of my knowledge, there is, I think, one FRB detection by LOFAR in the VHF range, somewhere above 100 megahertz. So far, no FRBs have been detected at even lower frequencies. The majority of the detections have been in L band and in the 400 to 800 megahertz range covered by CHIME.
Okay. Anybody else have any questions? More questions? All right. I want to thank you very much, and being our ambassador as a quote amateur radio astronomer and detecting FRB is a great accomplishment. So thank you and your team for undertaking this.